Thank you.
Very good.
Okay, thanks for all your help. So it's my third time, great pleasure to introduce Esra Bulbul. She's an expert in using X-ray observations of galaxies to constrain models of dark matter and dark energy, the, of course, two biggest outstanding questions we have currently in astrophysics and particle physics. So a few words about her background. So she received her PhD from the NASA Marshall Space Center, a Flight Center in 2010. Then was a postdoc at MIT, NASA Goddard, and at the Harvard Smithsonian Center for Astrophysics, where she was also staff scientist. And since 2019, she's been at the Max Planck Institute for Extraterrestrial Physics in Germany, and recently received a large ERC consolidator grant to build her group. And now she is the lead for galaxy clusters at MP, and also the lead scientist for the German Russian space mission called EROSITA, where she's leading the Galaxies and Cosmology group analysis. So we're excited to hear more about her work and that of her group. So please take it away.
Thank you very much, Marianne, for this nice introduction. And it's a pleasure to be here today to talk about EROSITA and the first results we got from EROSITA. I really wanted to visit NYU this time. My last visit was fantastic, and I had great fun and enjoyed talking with the faculty members and students. Hopefully, I will come back one day after all this COVID situation is resolved. So I'll tell you a little bit about the mini survey we have performed during the performance verification program of EROSITA and tell you what we've got from these first results. All right, but before we move on, I would like to give you a little bit of introduction about what we are going to talk about today. But for that, I'll take you way back in time. We now go back to very early on in the universe when the redshift was about 28. So we'll watch in this video how the structures in the universe formed at that time, and they evolved up to, we come to redshift of 0, which is today's universe. We are following in the box universe the dark matter particles, and they will show you how actually the matter was assembled. So in the very early on in the universe, you see the density field was very uniform and homogeneous, but then there you will see some density fluctuations, localized fluctuations in this density field, and that's where we will see the structures forming slowly. You see these fluctuations collapse on themselves, they virialize, and they form the structures that we see in our universe today. First, stars form, and then the galaxies form, and clusters of galaxies, which is the last leg of structure formation, are formed. And these galaxy clusters are, in fact, the largest collapsed objects in our universe, and they are located at the connecting nodes of these filamentary structures. So where you see these bright spots, those are these ginormous structures, what we call galaxy clusters. They are not, they are variable objects, but not in a sense that we see in other stellar objects. So for example, they don't vary from day to day or month to month, but their evolutionary timescales are about in the order of gigayears. So they slowly evolve through time. And their number density and distribution across the universe is a very good probe of cosmology, and that's why actually these objects are very important. So by counting their numbers and how they are distributed in our universe, we can constrain the basic parameters of our universe today. And let me introduce these objects to you a little more in detail. You can understand from their names, they are actually clusters of galaxies, so they contain galaxies, but that's not the major mass component we see these objects. When you look at one galaxy cluster in whole, the majority of the mass you cannot see, but it is in dark matter. So what we're talking about is about 85% of their mass is in dark matter, and we cannot really observe that matter through our electromagnetic spectrum. The rich ones typically contain about 1,000 galaxies. So if you look at one of these objects in optical light, this is a beautiful Hubble image. You can see its member galaxies. And this very bright one is called brightest cluster galaxy. It hosts the supermassive black hole, which can be active sometimes. But these galaxies, as I was saying, do not constitute the majority of the mass. So 85% is in dark matter, a few percent of the mass is in galaxies, and the rest, 13% of their mass, is distributed in a space between these galaxies. And that is what we call hot intracluster medium. And this hot intracluster medium is a very hot plasma. It is primordial, so it basically constitutes mostly hydrogen and helium ions. Its temperature can get up to 100 million degrees. It's so hot. And at this density and temperature, this gas is optically thin, and it emits primarily through X-rays through thermal Bremsstrahlung process. So it gives you a very nice continuum from thermal Bremsstrahlung. And on top of that, we actually observe some atomic transitions which come from some elements that enter to the intracluster medium through different physical processes. So these elements, metals like iron, silicon, carbon, calcium, and nickel, these are formed in galaxies and pushed out to the intracluster medium throughout the evolution of clusters through supernovae explosions or galactic winds or AGN feedback, etc. But the metals actually constitute about 1% of the ICM mass. So you can see that majority is really in hydrogen and helium. We can see this gas in the X-ray band because it emits a lot of X-rays. And we can then, if we scan the sky in X-rays, we can then localize and find these objects in the sky. And X-ray observations are one of the most efficient ways of finding these objects in the sky. And if we can find majority of them, large number of them, then we can reach to a statistical power to constrain our cosmological parameters. And that is the main goal of EROSITA. For the cluster science with EROSITA, we are actually planning or performing a large variety of science using these objects and EROSITA observations. Our main goal is to constrain cosmology. But EROSITA is also very good at mapping the large-scale structure, which I'll show you some results about that in a minute. And so we will publish a large number of papers mapping the large-scale structures in the universe. Because these objects are the most massive gravitational potential wells in the universe, they don't lose their baryons. So the metals or the baryons in general are locked up in clusters. So we have high redshift ones, we have low redshift nearby ones, right? We can basically observe the evolution of baryons within these massive gravitational potential wells. So that's one of the things that we have been working. But I am also very passionate about searches for dark matter in the X-ray band. We can also use these objects for dark matter searches because they are the largest collapsed objects which constitute enormous amount of dark matter. But we will not talk about dark matter specifically today because we didn't have enough time to for dark matter searches from the PV observations, but that is coming soon. Let's talk about EROSITA a little bit because you will hear a lot about EROSITA today. EROSITA is one of the two X-ray instruments on board of Spectrum Röntgen Gamma mission, SRG we call it in short. And SRG is a German-Russian collaboration. And you can see it was launched on this beautiful day in July 2019. It is right now in orbit in L2. And since that time, it has been operating very smoothly. And this picture, in fact, was taken just 1 week before the launch. You can see the satellite here, and the structure below is the other X-ray telescope called Arctic-C. Russian Collaboration built this telescope. It's a hard X-ray telescope, so it's sensitive from 5 keV to 50 keV. And our little EROSITA, which was built by Germany, which is not too little, as you can see in this picture, but this is EROSITA. It's a soft X-ray instrument. It's sensitive to 0.2 to 10 keV band. It carries 7 independent X-ray telescopes on board. You can see these telescopes over here, 7 of them. These are X-ray mirrors, and they focus X-rays onto the detector, which are basically at the back of the structure over here. So these are co-aligned in a way that they scan the same patch of the sky simultaneously. So we multiply our sensitivity by 7 by this way. So as I was saying, so it's sensitive to the 0.2 to 10 keV band, and it has an advanced design with no chip gaps. And that is very important for us to basically scan the sky smoothly. The detector technology is very similar to the one detector which is on XMM Newton X-ray telescope, currently operating in space as well. And but over that detector, we have basically no chip gaps. Our spectral resolution is much better, and we have a very low stable background. This plot shows you a comparison in the X-ray background. Blue and green are XMM Newton, which are taken in the same time period, and in red we see the EROSITA's background in different X-ray bands over here, and you can see we don't see much variability in the background. It's stable and it's low. This is very important because clusters of galaxies, which are the main goal of EROSITA, are very faint objects. So the fact that our background doesn't change much, it could be the gift of L2 orbit, and it is low, that we can detect many more of these objects, of course. Our noise level is low. And its large sensitivity, which I will show you in a little bit, is designed to detect clusters of galaxies. This is our field of view. We have 1 degree almost across. This is in comparison to the moon. This shows you the 2 X-ray telescopes which are functioning currently in sky. And you can see we have much larger field of view. And we are an all-sky survey. So we scan the sky in a very fast and smooth fashion. And this is our pattern. This is how we scan the sky. In comparison, for our grasp, we are 5 times more sensitive than XMM Newton and 100 times more sensitive than Chandra. This is our sensitivity curves, effective area in jargon, what we call, in the full X-ray band that we are sensitive to. And of course, there has been a large number of X-ray telescopes before we came along. But you can see our sensitivity curve, which is shown in red here, is pretty high. In the soft band, this is where clusters of galaxies mainly emit their emission. And above about 2.5 keV, our sensitivity drops. In blue is shown XMM Newton when you combine the 3 telescopes. The previous X-ray mission, X-ray all-sky survey, was called ROSAT. It went up in 1990s. Basically, that is shown in brown over here. And in comparison to the previous all-sky survey, we are 20 to 30 times more sensitive. And our, of course, spatial resolution is much better. And you will see that effect in a little bit in this image, in this video. I'll show you first the same patch of the sky, which was scanned by ROSAT in 1990s. And then we will move on to the XMM Newton, which basically can take pointed observations. So it can observe one small patch of the sky deeply at once. It doesn't scan as we do. And then EROSITA will come along in this video, and it will show you 30 years of advancement in X-ray technology, telescope technology, in 30 years in Europe. So this is ROSAT, and you can see the XMM Newton and small field of view, and this is what we got with EROSITA. It is remarkable. So EROSITA was led and built at MPE, and it's currently operated by MPE. All the rocket and RTX operations are done in Russia, but EROSITA operations are done at MPE. The EROSITA control room is 2 levels down below my office, and these are our operations team. And we move on to home operations because of COVID, and we are slowly coming back to office. And also the science is led by MPE. So you can see here in 2019, we launched. After 1 month of travel to L2, we immediately started our CalPV observations. And CalPV observations ended in December 2019. Since then, we have been scanning the sky. So our cadence is that we scan the sky, the full sky, once every 6 months. So we perform 2 sky scans every year. We are planning to perform 8 scans of the sky by the end of 23. We will be done with the all-sky survey, and that is going to get us to the numbers that we want for precision cosmology. We are right now here. In December, we will be finishing the 4th scan of the sky, and we slowly, step by step, release our data. So, for example, in July this year, we have released our early CalPV data. We have also released the software. Software is also built at MPE. And we have also published a number of papers with this early data release that we call it. And the all-sky survey data will be released as well in steps. So the first release will come around at the end of 2022, early 2023 timescales. We don't scan the sky homogeneously. Our scanning strategy basically is based on that we have 2 poles, what we call EROSITA poles, and they are the deepest places in our EROSITA sky. And our exposures can get up to hundreds of kiloseconds at the poles. But at the equatorial region is only, it will reach up to 2 kiloseconds at the end of the 8th scan of the sky. I lead the EROSITA clusters and cosmology science here at MPE, as Mariam also mentioned. This is my group at MPE. We work on cluster science mainly, and we are fully funded by ERC, but we also have partners in Germany. So we work with University of Tübingen, University of Bonn, University of Hamburg, and LMU and even AREP in France for science. And they provide multi-wavelength support as well as X-ray analysis. In this CalPV program, we have targeted 4 clusters of galaxies. These, what we call it, the first batch, the top panel, is the calibration program. For this calibration program, we just wanted to test EROSITA's performance. So we just took deep observations of several very well-studied clusters of galaxies, and they're perfect targets for calibrating any telescope if you have significant emission, because they just don't vary. Right, you need to wait for giga years for them to vary. So you can calibrate your telescope based on these observations of these objects. So we have compared EROSITA observations with XMM Newton and Chandra and Suzaku, but we find that in fact EROSITA performs really well, and our main observables were consistent with XMM Newton and Chandra with the observations which were performed before. So that was very encouraging. In the performance verification program, we have scanned two large area. So one of them was that video that I showed you, this about 339195 system, and the other one is a field which was in the equatorial region. I will mostly talk about this small survey that we performed today, but I cannot move on without mentioning this very exciting results which came from about 339195. You can see this is a merging system. So we see a cosmic web basically at work. I've shown you those pictures before at the beginning of the talk. It's exactly like simulations. So there are some southern halos. These are low mass groups which are falling onto this cluster merger system slowly along the filamentary region. So we expect the filament extending this way. And you can see the massive galaxy clusters. These are already merging, and this one is falling on top of this structure. And in the surface brightness excess, we have detected this 15 megaparsec long filament for the first time with a very high significance, about 11 sigma significance. And this is the longest filament known, and that clearly shows the ability of mapping large-scale structure with EROSITA. Okay, let's talk about this field that we performed also during the performance verification program. The idea behind this program was to test our predictions. We just wanted to look at, basically have a very quick look at the final depth we are going to reach at the end of the final survey in 2024, and see how many clusters of galaxies we are going to detect, if our predictions are on target or not. We just wanted to check this. So we scanned 140 square degree region at the equatorial region of the EROSITA sky. And the reason why we picked this region is because it's very well covered with other optical surveys. So once we detect an X-ray concentration, we can then determine its redshift and distance from us. And that is very crucial because we want to measure their properties, the properties from the X-ray observations. So in this field alone, we detected about 28,000 X-ray sources. And you can see its size in comparison to the moon in the sky. It's a really large region, actually.
So sorry to interrupt, but just to make sure, so we mentioned redshift measurement. So you get the redshifts from the X-rays, from Mars you detect, or do you need the optical redshifts, optical detection and then spectroscopy getting the redshifts?
Right, very good question. So from the X-rays, we can determine the redshift of these objects if they're very nearby. So we can extract their spectra because we now have the sensitivity in the full X-ray band. We can do that with EROSITA, but for very bright ones. We detect large number of very faint ones, right? So we can't really use X-rays all the time uniformly. For that, we use optical surveys. Most of our redshifts come from photometric measurements, but we also have spectroscopic measurements through SDSS and gamma in this field. So for example, when you look at an X-ray sky, majority of the sources that you detect is in fact point-like sources. These are supermassive black holes which are active. The dots that you see are all these supermassive black holes. But sometimes you detect these super fuzzy structures, and these are the clusters of galaxies you detect. So we detected about 542 of them in this field, and they look like this. And this particular one, I like it because it looks like a frog. And then if you go look at this exact same location in an optical survey. So we have Hyperstream Cam, and we have an MOU with the Hyperstream Cam group, and they have performed our redshift measurements in collaboration with us. And then from the photometric data, we could then determine the redshift and distance of these objects. So this video shows you how they are distributed in the sky and color-coded with respect to the redshift and distance. So the nearby low redshift ones are shown in large purple squares, and then very distant ones are shown in red dots. And this is very surprising to me, because we were not expecting to detect so many of these objects beyond redshift of 0.8. But as a matter of fact, the ROSITA performs really well, that we detect large number of them even beyond that redshift. It's remarkable. So this is a footprint of the Hyperstream Cam field in that same eFEDS region. It's taken in a small redshift slice. And so when we first detect an X-ray emission in a localized place, the first thing we do, we go to the Hyperstream Cam observations, determine its redshift. Then we start cleaning our X-ray data. This is a cluster. But there is a contaminant. This is an AG, an active galactic nuclei. These are supermassive, creating supermassive black holes. For me, they are my background. So I just cut them from my observations, get rid of them, clean my data, and it looks like this. And I further subtract the background. You can see the background here. So I subtract that background, and then I measure my X-ray properties. So the main observables from X-rays is the luminosity of the cluster. That tells you how bright this object is. And once you know the redshift, you can do that. And these are the luminosity measurements of that 542 clusters that we detected in this field. Overplotted is the flux limit of the survey. It's very classical for surveys. This means that below that line, we do not expect to detect any sources. So if there is a detection beyond that limit, it's either contaminant or the redshift of that object is wrong. But I wanted to stress here, this flux limit was first given in our science book in 2012. So this tells you we are right on target. So we will get to the numbers that we expected at the end of the 8th scan of the sky. And this shows you the redshift distribution in this field. Our redshifts are concentrated about redshift of 0.35, but we detect large number of high redshift clusters as well, which carries a lot of weight for cosmological measurements that I will show you in a little bit. When you're working on surveys, how well your survey behaves, how well you understand and characterize your sample is very important. Without that, in fact, you cannot do science. You need to know how well you detect these observations, right? That's called selection function. So for the construction of our selection function, we use state-of-the-art N-body simulations. We feed them with some embedded baryons in them to our simulator. So we simulate our entire EROSITA sky. We have the mock observations of all the objects that we expect to detect in the EROSITA all-sky survey. And these are showing you the source density of what we expect at the end of the 8th all-sky survey in our mock observations. Then what we do is that we run our codes with the same set of settings that we use in our observations on the simulations, on the mock observations, to get our observables. That gives us, for example, a probability of detecting a particular cluster with that redshift, luminosity, and mass. And that's what's shown here, and that's called selection function. So when the probability is low, right, we do not expect to detect anything here, so that these things that we detect over here in this band, right, they carry very little weight as opposed to the objects that we detect in this field. So this is very important to fold it in for the survey. And now I'm showing you the same plot, but overplotted to the selection function. And you can see that's in the background. And you see probably these are our contaminants, which do not really contribute to our measurements at all. One other great thing about the selection function, by using it, we can understand what is our completeness level and what is our contamination level. Right, so we have a lot of contaminants in this 542 extended sources we detect. They are really the candidates of clusters of galaxies and groups, galaxy groups. So these contaminants could be background fluctuations. These contaminants could be active galactic nuclei leaking into our samples. So what happens is that when you have 2 or 3 of them, our source detection algorithm gets really confused and thinks that it's a cluster of galaxies extended. And sometimes when there's so large clusters in the field, very bright, right, our source detection algorithm splits them into multiple sources. So these are all contaminants that we get in our sample. We want to get rid of them and have a pure cluster sample. And thanks to our selection function, we can do that. So at this, for example, full sample of the 542 clusters, we are complete at 40% level, and we are contaminated at 20% level. But the good news is that we can tweak some of the selection. For example, we have extent likelihood and detection likelihood. We can just adjust these parameters in a way in our sample to reduce the contamination and to increase the completeness using our selection function. That's a play that that's a game we play to basically based on our science needs. The other observable is the temperature, because now we have spectroscopic capabilities with EROSITA. And so we can measure about 20% of the sources, the temperatures of ICM temperatures, like this is the gas temperature of 20% of our sources, and you can see them over here. One other thing we looked at with the sample, we looked at their luminosity distribution. So this is what's called luminosity function. Within a given redshift slice, how many clusters that we detect within that luminosity band. And that luminosity function is a good probe of cosmology, although we didn't do cosmology with it. We just compared with the previous X-ray surveys to test our reliability and how we perform. Our measurements are plotted in black data points over here. So with XMM Newton, there were several small-scale surveys which were performed before, 5 or 6 years before, and they are overplotted with the colorful bands over here. And you can see we do really well, and we agree with XXL, which is coming from XMM Newton. The other thing, we just wanted to see if we can do any cosmology with the numbers that we have. And we didn't have so many clusters in the small field of view, but we basically divided our sample to the 2 subsamples and looked at the redshift evolution, right? That can be used to constrain cosmological parameters, but we didn't really detect significant redshift evolution. When we look at the different redshift slices, we see that we are consistent with XXL and WARPS. These are other small area X-ray surveys. We will do this for all sky survey, and you will see maybe next time our numbers will significantly increase, and that's when we will have some hope of determining the cosmological parameters and evolution, hopefully. The other thing is we then, after detecting and knowing the luminosity and a gas temperature of these clusters, we characterize them. Sometimes clusters can be mergers. Sometimes they can be standalone, relaxed, boring-looking clusters. We like these boring-looking ones because they behave really well. And we want to use these in our cosmological measurements. But first, we need to distinguish which ones are good looking, which ones are very disturbed looking. We have developed a method now. We look at very different properties based on the 2D images. For example, we look at how the electron density is distributed in a cluster. We look at how concentrated the X-ray emissions. So you can see these are very concentrated. And how elliptical is the emission. And then we look at the cuspiness of the X-ray emission, overall X-ray emission. We look at how the photons are distributed at the large scales. Based on these properties, we determine if this is a merger, messy looking merger, and this is a boring looking cluster that we want for cosmological measurements. So that paper is now out, and you can view that. And using that information, we can look at the evolution of baryons. So that's also what we have published earlier this year. We looked at the number density evolution with redshift and luminosity for the first time. So now we have large enough clusters which covers large enough redshifts and large enough luminosity range that we can constrain their evolution. And as a matter of fact, in comparison, you can see our bins here in orange in number density as a function of redshift and luminosity and redshift here. In comparison with the previous radio Z surveys, and they are sensitive to very bright, massive clusters, and we can basically probe down low luminosity, low mass clusters and galaxy groups at the same time. And we can constrain the evolution of baryons in another way in these deep dark matter potential wells very accurately. And so this was the evolution, and I would like to talk a little bit about the large scale structure. This is also a very surprising result that we came up with. Maybe it should have been obvious, but I think we were just so focused on cosmology, we didn't realize the power we had. EROSITA can detect lots of low mass halos. These are galaxy groups, and they are located in the filaments, right? So we actually look at the simulations. We are sensitive to all these low mass halos. So when we map them, right, we can map the large scale structure. So we realized this when we were looking at eFEDS observations. We saw that in the very edge of the survey, these 8 galaxy clusters were connected to each other. So we looked at immediately to hyperspring-cam observations. As a matter of fact, yes, they are at the same redshift. So they are part of the same filamentary structure, and they are collapsing on themselves. And in giga-years of time, they will form this massive galaxy cluster. We just caught them giga-years prior to that stage. And when we searched the entire field, we have found 19 of them in this small region of the sky. So that shows you just alone the power of EROSITA to map the large scale structure. And these are the very massive ones. So first one was published as a separate paper earlier this year, and our catalog paper involves the other 18 months. But so the elephant in the room is cosmology. We haven't done cosmology with the small region, and because we didn't have numbers, constraining numbers, but that's what we're working on currently with All Sky Survey. But the building block to cosmology from EROSITA observation goes through the mass calibration. So we need to, after determining the X-ray properties of these clusters, and the number, the distribution of the clusters, we need to somehow connect that information to the mass function, which is a very sensitive probe of cosmology, right? So that means we need to know the mass of each cluster in our sample that we detect. There are various ways of doing that. We could use optical data, but we don't have homogeneous coverage in our sky. And also optical richness is not a good proxy for mass. There's a large scatter, so it's really not good enough for us. We could use our own X-ray observations to measure the mass of clusters, but the problem there is that we have to assume some fundamental things. For example, we have to assume that the gas is in hydrostatic equilibrium with the gravitational potential when provided by the dark matter. That's a big assumption. So majority of the clusters, maybe boring looking ones, follow this assumption, but we know from indirect measurements that not all of them follows this assumption. So we don't want to bias our result. That's not good enough for us either. The currently best method is to use weak lensing observations, follow-up observations of our clusters through 3 different surveys, DES, KITS, and HyperSpringCam. And we have MOUs and external collaborator agreements with these surveys. So when we detect a cluster, they go measure their mass from their weak lensing observations. And we build the scaling relations, we build the mass function and determine cosmological parameters that way. And the first proof of the concept study was done for the eFEDS field. That is also published earlier. So this is a luminosity that we get from eFEDS observation as a function of the mass that comes from weak lensing observations from HyperSpringCam. And you can see 542 of them, a little less here because we clean the contaminants. We could measure the masses of these objects, majority of these objects. So then we can take it 1 step level further and constrain cosmology. And as a matter of fact, EROSITA is very complementary to other cosmological probes, and we probe a very unique mass range in comparison to other cosmological probes. Here, low mass regime. And this shows you how that mass function is sensitive to cosmology. So for example, if there is no dark energy whatsoever, and if your universe is just consists of just matter, you would get a mass function which is shown in red. And if there is a 70% of dark energy, you would get a mass function which is shown in green. The idea is to fill this plot with EROSITA data points and then come up with fundamental cosmological parameters. So at the end of the 8th survey, we are going to detect more than 100,000 clusters. When we play this game, mass function game, with them, we will obtain sigma 8 and omega m. This is the density of the matter, and this is the normalization of the matter density in a percent level precision. So it will be competitive with other cosmological probes, which are the 4th generation cosmological probes. And the other things is also we look at the other scaling relations to measure the evolution of some of the fundamental properties, X-ray properties and thermodynamical properties. This is my student Emre, who just submitted his paper today, and you can see the evolution of luminosity and temperature for the clean sample in the eFEDS, and in comparison with the other results in the literature. And our results are basically very consistent with the previous results in the literature, and that shows the fidelity of our products. And one other thing we discovered is that some of the clusters of galaxies, in fact, leak into other catalogues. So that we have point source catalog, which consists of mostly that dot-looking objects, these active galactic nuclei. Some of our clusters are so underluminous and so compact that they actually go into that catalog, and we miss them in our catalog. And we found a number of them through our optical observations. This one looks very, very point-like source. And the reason is that there is a very bright active galactic nuclei in the center. So we found about 357 of them in the field. So you just add 547 with 357, that gets you up to 900 clusters in this small region of 140 square degree. You can see the number counts that we're going to get. It's amazing. And then when you look at the radio observations, you immediately see that this active galactic nuclei is in fact there and very active. And these kind of objects, in fact, are good for dark matter searches, like very light dark matter searches, axion-like particles, and also studying AGN feedback. We are showing you here in blue this sample of clusters of galaxies which have bright clusters or so compact that we missed, in comparison to the extent selected, which is in gray. We also find very interesting clusters like this one that I showed you earlier. These are very rare mergers in the sky. They are very massive by themselves. They are good probe of testing lambda CDM because we do not expect to detect more than a handful of these objects. And we found one in the eFEDS field. And it looks very much like Algordo, which is also in our part of the sky, and Bollet. So we are currently studying this object, measuring the mass using our multi-wavelength data, and we will publish that paper very soon. But I would like to show some exciting results from the All Sky survey, because that is what we are aiming and working on at the moment. In 1995, X-ray sky looked like this with ROSAT. Now in 2020, we got this with EROSITA. It's really beautiful. You can see the nice details and structures. You can see the active galactic nuclei point sources, which is 88% of the X-ray sources here. You can see the EROSITA bubbles that we published a Nature paper earlier this year. But also you can see these nearby bright clusters in the sky. That's, for example, this is a Virgo cluster, which are taken by Chandra observations. It's remarkable. In this full sky, we have detected more than 20,000 extended sources out to redshift of 1.5. By the way, I have to say, in Germany, we own the data rights of the half of the sky. So southern sky is ours, northern sky is belongs to the Russian collaboration. So this shows you our part of the sky. We detected 12,000 extended sources over here, and 1,500 of these clusters are known. We have detected, that means 10,000 new extended sources in our sky alone. And this shows you the redshift distribution focused on one place in the sky. And we have a very rigorous way of determining their redshift. So we ingested large number of X-ray optical surveys in our follow-up code, which called EROMapper. And as soon as we detect an X-ray cluster, we go look at these public surveys in the PhotoZ and measure their redshifts. And then we follow them up with SDSS5 to measure their redshifts accurately in 3 dimensions. And this is very preliminary result. It's a luminosity, the performance verification program of EROSITA was a success. It basically showed that we can meet our targets at the end of the All Sky survey in 2014. We have, from just the clusters and cosmology working group, we have actually published more than 14 papers now. This number needs to be updated because we just submitted a few more. And that data is now public. So if you would like to play with it, you are very feel free to download from our webpage. And if you need any help, please contact us. And currently we are using in the first All Sky survey, and that data will be made public eventually. And yes, stay tuned. And thank you very much for your attention. I am happy to take questions now.
Okay, thank you so much. It's a beautiful, beautiful data, and it's so amazing to see the high resolution aspects of it. I have a few questions myself, but I'd like to make sure if others have questions, please use the raise hand button. Okay, so one question I had was, so you mentioned one tool for cosmology, which is the number counting, right? The mass function. Now, what about, are there any thoughts about doing a kind of 2-point correlation function for Baryons related cosmology? Kind of the spatial distribution, since you have also higher spatial resolution.
Right, so we do have a plan for that. So from the clustering and AGN clustering, I think that's what you mean, right? We do plan for that. And as a matter of fact, we have some predictions. It will be as competitive to the mass function experiment by the end of the EROSITA All Sky survey. So we are planning to publish those papers as well.
Another question I had was, you mentioned the cadence, which is twice a year, right, for the whole sky. Are there any cadences that are faster for time domain astronomy, right? Because, you know, this is a beautiful, very sensitive, wide field X-ray telescope. And for aspects for time domain astronomy, like shock breakout, GRBs, right? Since we have very few, you know, GRB telescopes ever, and it's basically SWIFT, that's kind of, you know, very old and, you know, getting older. And sadly, as you know, right, the X-ray astronomy community in the US kind of had put in proposals, but I didn't make it to the next round. So basically in the US, at least, kind of that's lacking. But so curious to hear about time domain astronomy with EROSITA.
Right, so because we cannot, we are in the process of scanning the sky, right? We can't really point the telescope and go somewhere else where we see the variable sky. But that place in the sky, that particular location, which is varying, let's say, is visited every 6 months. So we have a variable source working group. And they are working on these variable sources. They are basically in collaboration with other X-ray telescopes, as you say, it's SWIFT and NICER and other also ground-based telescopes. As soon as someone detects something, they look at immediately EROSITA to EROSITA data. Yes, I know that they're working on it, but of course, within the limitations that we have in terms of the schedule of the observations.
Okay, so if there are no more questions, let's thank Esra again. And thank you so much for your talk. And I will stop recording.
Thank you very much.
We can also stay on and talk a little bit if you have a few more minutes, because I had a few more questions.
Okay. Sounds great. Thank you all.
Okay.